Okay, so this is forces 2. The whole point for 2 is to get us ready. Take a problem, draw and label all the forces on every object in the problem, that into a Newton's second law equation, and either solve it using the easy way or the hard way. So, again, we have a situation where we have mass 1, mass 2 on a table where there is no friction. Hand is pressing down on a mass 1, hand is pressing down on mass 2, mass 3, and mass 4 are hanging. Looking at the forces on those objects, I want to know which force can't be acting on M3 and M4. M3 and M4 are hanging, which means they're not touching a surface, which means I can't have a normal force on M. Now we want to take these free body diagrams and match them to the objects that we have there. So the first one is for an object that has tension pulling up and pulling down, force of weight pulling. The one that has a tension pulling up and a tension pulling down is. The next one has force pushing down on it and a normal force pushing up. So this right away tells me we're talking about mass. Weight down, one tension pulling to the right. That's one. Next one has force down and the normal force up. So I'm back on the table. Tension is pulling left and right. That's mass 2. It's got a string pulling to the left and a string pulling to the right. Last one just has tension up, weight down. That's mass 4 with nothing else going. 2, I got a man pushing on a 12-kilogram object for 10 seconds, 8 meters to the right while he's pushing it. First thing we want is the acceleration. We have enough information here. Going for 10 seconds, 8 meters. The time is 10 seconds. Displacement is 8 meters. We start off with an initial velocity of 0 and we want to accelerate. Equation that's got all those in it, x equals squared. Velocity is 0, so it goes away. Twice the displacement times squared is my acceleration. N times 800 squared leaves me with 0.16. That's my acceleration. Now, if I want to calculate the man's force, he's the only force acting on it, so it's really easy. Got 12 kilograms. Giving me a force so man's pushing it, pushes it his 8 meters, gets to velocity 2, which we know kind of what those numbers are. Surface is frictionless. How does velocity 3 compare to velocity 2? Man, let's go at velocity 2. No friction. Those speeds are going to be the same. No friction, no slowing down. Slow without any friction. The surface has friction. How do they compare? Well, if the surface has friction, then the object's going to slow down between V2 and friction is what's going to slow it down. Without friction, it would go on forever. Okay. Next one, we're taking forces and we're categorizing them into a contact force, a force where objects have to be touching something else in order to experience a force, or a field force. So, tension. There must be a string touching my object for tension, contact force. Normal force, we must be on a surface. For the normal force, we must be touching the surface. Can cause accelerations. Any force can cause an acceleration. Gravity is a field force. Electrostatic force is a field force. We don't have to be touching. All right. Here's Newton's third law. It says for every force is an opposite force. Opposite force has to be the same type, right? My action force is a contact force. My reaction force. Got a box sitting on a table. Normal force is the table pushing up on the box. Reaction to that has to be the box pushing down on the table. Okay? The same two objects box and the table. Same type of force. Pushing normal force. Same two objects, same type of force. And one force acts on the box, the other force acts on the table. Acts on different objects. So gravity pulling down here cannot be the reaction to the normal force pushing up on the box in the Newton's third law action-reaction vocabulary, because gravity would be pulling down on the same object. It still acts on the same object. And gravity is a different kind of force. For that reason, it's not the one that opposes the normal force in the Newton's third law way. Part B, what force opposes the force of weight pulling on the box? So the force of weight, the force of gravity, is the force of the earth pulling down on the box. So the reaction to that is going to be the force of the box pulling up on the earth. Works the same way, right? That's a gravitational force pulling back up on the earth, the same kind of force. Weight is the force of the earth on the box. You need to write that down. You need to know it. Everything else is still the same, right? It's still the same kind of force, still gravitational. It's still between the same two objects there. It acts on different objects. All right. 5 with the tiny people pulling on the box. So we know that T is for tension, Fg is for weight, Fn is for normal force. So let's go through this. F1 is the force of the two men pulling with the rope. F1 with the rope is going to be tension. The force pushing up by the floor, that is the normal force. F3, the force pulling down on the mass, the gravitational force. Now, when we write the gravitational force, I want us to write mg when we have the mass, because the gravitational force is defined as the mass of the box or the object times the acceleration due to gravity. So when we write mg, it's a hint telling us how to calculate the weight of the box. We need to be meticulous about that. Force 4 is the force trying to stop the mass from moving. That's going to be friction. Now, the next part has us going through what direction they're pointing in. Positive x is always in the right. Positive y is always up. So if it's in the negative x direction, it's pointing backwards, pointing to the left. That's force 4. So it was the force of friction. Positive y direction was force 2, pointing up, the normal force. Positive x direction is force 1. That's the guys pulling forward, or tension. Negative y direction is force gravity pulling down, again, which we need to remember and write as mg. So, part I, which forces would be used in the equation net force equals mass times acceleration in the y direction? Y direction are the positive y, negative y thing. Net force in the y direction would be those two forces. Normal force minus the weight. That's how we would do net force in the y direction. Then, net force in the x direction equals mass times acceleration in the x. In the x direction, the net force would be the force of the men pulling, tension, minus the friction. That's how we build Newton's second law equations. That net force in the x, that sigma force in the x part, is telling me to add up all of the forces in the x direction. Question 6. The mass is hung over the pulley. So for that, we can identify the forces shown below. So force 1, the force pulling down on the 2 kilogram mass, is the weight of the box, gravity. Again, we're going to write that as m1g. Force pulling up on the 2 kilogram mass is tension, because it's a string. The force pulling up on the 8 kilogram mass is also tension. It's the same string around that pulley. force pulling down on the 8 kilogram mass weight into G. At that point, that's going to get really helpful because now we are distinguishing between. So, which two forces are equal? That's going to be the tensions. Tensions are equal to each other. Then the next part is calculate the forces. Force 4. Force 1 is mass 1, 2 kilograms, times the acceleration due to gravity, so it's 20 newtons. Force 4 is mass 2, 8 kilograms, times the acceleration, 10 meters per second, 80 newtons. Force 2 and force 3 are both tension, and they are the same. They are equal to. So in this case, tensions are equal. Force 1 is 20 newtons, 80 newtons. All of my forces are in the y direction. None of my forces are in the x direction. I want to know which way the system accelerates. It's going to go with clockwise. Essentially, the 8 kilogram mass is going to go down because it's larger. Larger force. 2 kilogram mass is going to go down. Larger force on the 8 kilogram. Right? So it accelerates with the 8 kilogram object. So if we look at the 2 kilogram mass, it's accelerating up. That tells me that force 2 on that mass is larger. Object accelerates up. Which force is bigger, force 3 or force 4? The 8 kilogram object accelerates down, so force 4 has to be larger. That's my direction of acceleration. So I'm going to find the acceleration of the system. I'm going to straighten it out. Two kilogram mass, we've kind of swung it around to the left. Now tension pulling that way, M2G, 20 newtons. It's connected to the 8 kilogram mass, pulling back in that direction, 80 newtons in that direction. For the easy way, we're going to cross out those similar forces. We're going to combine our masses. When we do that, the tension goes away, combining our masses. Looking at this thing as one big system of 10 kilograms. Since that tension is between those two objects, it goes away when we're talking about the entire system. We've got 10 kilograms now. Pulling to the right, we have 80 newtons. Pulling to the left, we have 20 newtons. I can really easily see that my net force on this thing is 60 newtons to the right. So the acceleration is going to be the net force, 80 newtons minus 20 newtons over the total mass, kilograms. That acceleration comes out to be 6 meters per second. Yeah, okay. Soon, yeah. All right, so for number 7, child on an elevator, we want to know what's going on in each situation. So before we start, best bet is to draw a free body diagram. Picture of the forces acting on him. So we have a 40 kilogram boy. He's standing on the elevator, so he has this surface normal force pushing up, and he has his weight pushing down. Now, for part A, the acceleration is 0. So what that tells us is that we're going to have constant velocity. That's how we know, is because we have constant velocity. So when the acceleration is 0, when I have constant velocity, my net force is equal to the normal force minus the weight, but all of that's equal to 0. Okay. The net force part of that is putting the normal force minus the weight together. And because I have 0 acceleration, that means I have a net force of 0. That tells me that the normal force is equal to the weight. So in the case of moving at constant velocity, or in the case of being at rest, whichever direction we're moving, or if we're at rest, the normal force is going to be equal to the weight. Those forces are going to be balanced. Now, for the elevator accelerating upward, the net force part still looks the same. I have the normal force minus the weight, but instead of equaling 0 this time, because we're accelerating up there, it's equal to mass times acceleration. So when we solve for the normal force, we just add mg to both sides. First off, it tells me that the normal force has to be bigger than mg. There's an unbalance in the forces, and if we're accelerating up, it's in that direction. So because the acceleration is up in the direction of the normal force, the net force, my excessive force, must be up as well. Now, the last part, we're accelerating down at 5 meters per second squared. So in this case, it's going to be mg minus the normal force. And this is because we're accelerating down. So if this is my object, the weight is down for the object, and the normal force for the object is up, just like before. The free body diagram hasn't changed. But in this case, the acceleration is down and the weight is down. Right? So if both of those are down, if the acceleration is down, then the weight has to be positive. That's why it's mg minus the normal force. The normal force is in the opposite direction of the acceleration. So in this case, mg has to be bigger because the acceleration is down. My net force is down opposite that as well. So mg minus the normal force is equal to ma. So if we're going to solve for the normal force, we subtract ma from both sides. We add the normal force to both sides. So mg minus ma is equal to the normal force. I want us to calculate it. So 400 minus 200 gives me the normal force as 200. Now, in the case of the elevator accelerating down with the acceleration due to gravity, that would mean the elevator is in free fall. And if the elevator is in free fall, that means the only force acting on the boy is weight, and the normal force has to be 0. That's one way of looking at it. Another way is to take that. Let's go ahead and write that down. At 10 meters per second squared, the elevator is in free fall, and the normal force equals 0. Because it's in free fall, the only force acting on it can be weight, not normal force. Another way of looking at it is to take the equation mg minus ma, because everything else is true, I just have a different size acceleration. Say, okay, I got 40 times 10 minus 40 times 10 equals a normal force of 0. We can do it mathematically as well. All right, here we have what's called an Atwoods machine. It's 2 masses strung over a pulley with the same string. So to start, we're going to draw all the forces on each mass. So tension is up 10 kilograms, has weight down on it. We're going to go ahead and calculate that weight. It's going to be 100 newtons. And then for the 20 kilogram mass, I've got tension up and weight down, m2g. And again, that's how we're going to describe weight every time, m2g. We're going to go ahead and calculate that. It's 200 newtons. Since 20 kilograms is bigger, the 10 kilogram object's accelerating up, the 20 kilogram object is accelerating down. We're going to go ahead and do the easy way, which is where we line up our accelerations to be in the same direction. So we tilt that 10 kilogram object to where its acceleration is to the right. That means its tension's to the right, and the weight of 100 newtons is down. We'll do the same thing with the 20 kilogram mass. We'll tilt it to where its weight, 200 newtons, is to the right and the tension's to the left. And we're going to combine these two things down into one object. When we do that, the tension, which is in between those two objects, which is holding our system together, becomes an internal force for our system. So those tensions cross out. I got 30 kilograms with 200 newtons one way and 100 newtons the other way. And once we have the system drawn like this, where it's just one object and then the non-canceling forces that act on it, we're going to say acceleration is equal to net force over mass. So my net force here is 200 newtons minus 100 newtons. My total mass is 30 kilograms. So that makes the acceleration 100 newtons over 30 kilograms, or the acceleration is 3.3 meters per second squared. We also want to find the tension in the string. So to do that, we're going to have to take one of our objects, and we'll do it for both, and write out the Newton's second law equation for that. I need you to be able to write out the Newton's second law equation for that, but we've already been doing it. So we're going to take that first, the 10 kilogram object, and say, okay, the net force is all of my forces added together. So that's going to be tension minus the weight, because the acceleration and the tension are in the same direction. So tension is positive and weight is negative for this object, and that's equal to m1a. That's the Newton's second law equation for that mass. You have to be able to write that. And so we have tension is equal to m1a plus m1g, so it's just plugging in and doing math. So 10 times 3.3 plus 10 times 10 gives me a tension of 133 newtons. All right, because we need the practice, we're going to do it for the 20 kilogram object as well. There's an important change. Here the acceleration is down, so it's going to be the weight m2g minus the tension. The reason is the acceleration's down, so the force with the acceleration is going to be positive, and the force against the acceleration is going to be negative. And it's going to be equal to m2a. So we solve for tension, m2g minus m2a. And that's going to be 20 times 10 minus 20 times 3.3. And that tension comes out to be 134 newtons. So they're a little bit different because of rounding, but that's it. All right, question 9. I'll write that down, rounding. All right, so question 9, new system, same plan. We're going to write down all of our forces. So m1g is down, that's the weight. We write m1g because it's telling us how to calculate that force. m1, 12 kilograms times g, 10 meters per second squared, 120 newtons. Pulling up, we have tension, and we're going to call it tension 1 because I see that there are 2 strings. We're going to move on, do the same thing to the 5 kilogram mass. I see a string pulling on it, so I know that one tension is pulling to the left, another tension is pulling to the right. The weight is pulling down. We write that as m2g. That's going to be equal to m2, 5 kilograms, times g, 10 meters per second squared, 50 newtons. The normal force is up. And then the 20 kilogram mass has that same tension 2 pulling up on it. And then we're going to call it m3g, or 200 newtons pulling down. And again, m3g, we write that because it's m3 times g, 20 kilograms times 10 meters per second squared. I'm going to go ahead and draw in the direction of acceleration. Since the 20 kilogram object is bigger, accelerates up, over, and down. So we're going to take and line everything up, kind of redraw the direction. So 120 newtons now pulls to the left. We don't really have to change anything for the 5 kilogram mass. And then the 200 newtons pulls to the right. And we've got the direction for acceleration on everything. Now, what we see first is that for the 5 kilogram object, since the acceleration is to the right, that up force and that down force have to balance each other out. What that means is the normal force equals 50 newtons. Tension 1 pulling both ways on 2 different objects is a third law force pair. We can cancel it out. Same thing with tension 2. Same force on different objects in different directions. When we combine that into the system, that's an internal force that we can cross out. Those two 50 Newton forces balance each other out. That's not Newton's third law, that's Newton's second law. And so when we redraw this, we have all the mass together, 37 kilograms. 200 newtons pulling to the right, 120 newtons pulling to the left. So the acceleration is the net force over the mass, 200 newtons minus 120 newtons divided by 37 kilograms. It's 2.16 meters per second squared. Now we're not done. We need to find the tension in each string. So we're going to take our 2 hanging masses and do Newton's second law for those. So for that one, the net force is T1 minus M1G. That's going to be equal to MA. The reason for that is that tension 1 and acceleration are in the same direction. So T1 is mg plus MA, so we can plug in our numbers. 120 plus 12 times 2.16, that makes T1 145 newtons. We're going to do the same process for this, but net force this time is going to be M3G minus tension 2, because the acceleration is down for this object. So that's telling me that M3G is bigger this time. It's winning the tug of war. And that's equal to M3A. We solve for that. That's M3G minus M3A. Tension 2 is 200 minus 220 times 2.16. And tension 2 comes out to 156.8 newtons. And it's okay that they're different because